Welcome to the to this third workshop of the Datathon Machine Learning Competition on Anti-Semitism. This is a webinar sponsored by the Institute for the Study of Contemporary Anti-Semitism at Indiana University. And I'm very happy to be here with my two friends and colleagues, Katharina Sommer, who is the project coordinator, and Professor Damir Cavar, who will be leading this workshop today. Damir Cavar is an associate professor here at IU in Bloomington. He's teaching and researching computational linguistics, natural language processing, so NLP, and AI using classical quantum computing. He directs the NLP lab here at IU and the Quantum NLP study group, and is a core faculty member at the Luddy Artificial Intelligence Center. I hope I didn't forget some of the most important things, but you have a number of roles here at IU and beyond. But I understand you also have a slide where you have your contact information, so that is great. We're really happy that you joined us here in the program and explain the topic of today, automated content detection, the basics. And we would like to use this, of course, to improve automated detection of anti-Semitic speech for our analysis. And you have been working on these kind of things for some time. This is the third time that we're doing this kind of competition together with the Datathon and machine learning. And so we have two parts in this workshop. So the first one is a public workshop. So there will be a presentation for about 40 minutes, 45 minutes or so. We will see how long it takes. Then there is an opportunity, of course, to join us with for the Q&A. And then we have a coaching meeting for the participants only of this competition. With that, I hand over to you, Damir. Thank you.
Yeah, thanks a lot for the invitation, and it's an honor actually to participate in these. We did that indeed like 3 times so far. We started back then in 2020, if I remember correctly. And we had participants from all over the world, actually, which was quite interesting. And they had very good ideas and came up with very good solutions. So we hope that, in this context, we'll have sort of similar effects. And I hope that you all enjoy doing this. And this is also the goal of this presentation today. I'm not going to lecture deeply into all these methods and technologies. I will show you very concrete examples that I rather use and teach as templates to students that they can then use and develop and change for their needs and so on. It's just often the case that you miss, basically, if you search online and you even ask ChatGPT for some suggestions how to solve some coding problem, that you don't get what you need, actually. So these examples that I will show you today are basically supposed to just guide you directly into starting the work and starting to do experiments with classification of anti-Semitic tweets and social media content. We agreed that you can raise your hand and you can put in the chat questions that we can immediately answer. You can interrupt, and I'm happy to stop and answer the questions first before I continue. There's a GitHub repo that you can access that has all the Jupyter notebooks that I'm using here in this lecture, and the slide deck as well. On the slide deck, I will present you basically just core information, and we'll then go through the Jupyter notebook in a practical example session, so that you get not just the idea about what these algorithms and tools do, but also see how you can actually apply them directly and with immediate results. So let me share the screen, and we can go straight into this. Let's share the full screen, basically. It's the easiest. And hide some of these things here. Hide video panel and the floating menu. So you see my screen, everybody?
Yes.
I can see, yes.
Okay, good. You see, I'm not a PowerPoint expert, but I had to choose this because of the presentation style with Zoom. So we're talking about anti-Semitism detection in social media. And in general, basically, this is a sub-problem of, I would call it hate speech detection in social media in general. And you will find, if you search online, more on hate speech detection and technologies and techniques than on anti-Semitism. And so right now, what I want to do is basically just go and tell you how you could reach me, who I am, where I am. And I will point you to some research resources, which is in particular sort of the way I try to guide students to work on these problems is to point them to literature and let them read some papers, most recent, maybe sometimes tutorials and summaries about state-of-the-art solutions for certain problems and challenges. I'll show you where you can find those. And these resources are either literature, papers, publications, or code and data sets that you could use. And then we'll go through the goals, and I will show you a little bit about the methods, introduce you basically from old classical probabilistic classifiers to state-of-the-art generative AI and large language models. I'm associate professor, as Günther already mentioned, focusing mainly on natural language processing, which is some people call it computational linguistics, some people call it natural language processing. NLP tends to be the term that people use more when they are talking about industry and engineering solutions. Computational linguistics more if it's about theoretical linguistic problems and so on. So I'm into both. There's a website link here, the NLP Lab, where you can find a lot of resources and our publications, and you can see how to contact me and some other members of the NLP Lab who are into all kinds of different projects, who are also interested in hate speech and anti-Semitism as well, actually, and links on AI and quantum computing for natural language processing as well, which is, it sounds hyped and so on, but it's an interesting different paradigm for thinking about how to solve natural language problems. So you're welcome to get into that and get in touch if you're interested. Follow the link to my website, and you will find also ways to contact me there. The literature and the main literature that I recommend, if you haven't been working on natural language processing issues so far, is Jurafsky and Martin. The third edition of the textbook is freely available online at this link, Speech and Language Processing. You can download the individual chapters, and you can download actually slides that go, teaching material that goes with these chapters. And I could actually probably just open this. Do you see the website?
Yes.
Okay, good. So here you see basically a nice overview of using models like Ngram language models, naive Bayesian text classifiers, logistic regression, and so on, and then vectors and embeddings, and then transformers and large language models. And this is exactly sort of a way how I will guide you through not going into the details of the theories and the textbook as such. Just, go in there and read it if you're interested in a very particular method. That's the most excellent, best textbook that I'm aware of. And I'll just give you the code that goes with that is not part of the textbook, that is missing, so to speak. And the other resources that I usually use myself when I search for articles and publications in a specific domain is Semantic Scholar, Archive, and the ACL Anthology. So in Semantic Scholar, if you go and open up this link here, it will show you a list of published articles that are classified as related to anti-Semitism. And if you scroll through this data set, you will find, for example, our colleagues here who are organizing this webinar and this challenge have publications in there as well. And some of those publications are technical, some are theoretical and describing the problem and discussing it as such. You could go ahead and also just search for hate speech in the same resource, and then you will find far more papers and articles about automatic solutions and so on, about technologies used for detection of hate speech and anti-Semitism. Another important resource is, of course, Archive, and there you will have the same kind of look for anti-Semitism there. Of course, you will find then, again, papers published by the colleagues here who are organizing this webinar here, and various other technical solutions. So this resource here on Archive is actually far more technical, where you will find very interesting discussions about classifiers, how people recognized certain kind of toxic and hate speech towards, say, Jews or other minorities in general. And another good source for really like peer-reviewed articles and publications in the NLP domain is the ACL Ontology. This is the Association of Computational Linguistics. And you'll see that there are some publications. It's not a lot, but there are a bunch of publications that are interesting. More recent, actually, over the last 3 or 4 years, the number of publications was growing actually in this domain. If you search for hate speech, you will find far more of these articles that have sort of technical sides to them. That's a good resource to start with to identify literature. And if you are working on a project, it might be, worth a publication or considering putting a real paper together about your results, which means that you will want to have an overview of what did other people do in that domain and how did they try to solve this, and why is your method interesting or better, and so on. Good. And there's a lot of stuff in the chat already. Okay.
That was me just posting the links.
Right. So hopefully the slides, you can download them on GitHub and then have all the links, and hopefully they function. If there's any issues with that, let me know. This is the repo on GitHub where you will find the Jupyter notebooks that we'll go through today. It's annotation portal on GitHub, and the Datathon and Hackathon GitHub IO sub-project or repo, where you find the instructions and so on. But in the code section, you will see in the README file some links to resources, and then the links to the individual notebooks that we'll discuss, some briefly, some more detailed. And we'll experiment a little bit with some of the large language models in the end to just show you how you could utilize these models and test things with them. There are a bunch of other GitHub repos. My particular GitHub repos are full of material that you might want to use. It's a little bit chaotic. If you go to my personal GitHub, there are hundreds of repos, but the Python tutorials that I'm using, that's a nice collection if you're sort of beginner in the computational linguistics and natural language processing domain. And there are a lot of notebooks that explain you certain kind of techniques and technologies that you could use for these kind of problems, classification and extraction of information from textual sources. And there are a lot of GitHub repos actually that mention anti-Semitism that I didn't study in detail, but there are some that talk about automatic detection and so on. And I recommend, search around, check what other people are doing. And when you develop your own strategy for your project, you could benefit from that and maybe start from some existing sub-project and improve your own solution that would speed up the entire work. Kaggle is another data scientific type of platform where sometimes companies, sometimes research projects and so on post challenges with data sets and tasks and let teams compete, and you can win a prize if you have a good solution and so on. And there are some data sets you can find there and code and solutions that people developed to solve the challenge or the problem that was posted there. There are various other such similar sites, so you'll be able to find that yourself. Now the goals for today, what I want to go through is basically just general sort of discussion about how to process text and tweets in particular, and how to extract frequency profiles, and then estimates of probabilities of probability distributions from these frequency profiles from textual corpora data sets. And then how to use those in machine learning applications like Bayesian models, or logistic regression and linear classifiers and so on, or how to use transformer models, which is more popular now, for example, with a BERT model or some derivatives, some models that are sort of similar to BERT or just extensions of BERT, tuned BERT models, to apply, classification, extraction of information, and so on. And then we will look at large language models and generative AI like OpenAI's GPT and Claude 3, not from what you might be familiar with, the text interface, the website interface where you directly interact with this model, but using Python and Jupyter notebooks so that you can actually submit a batch process and submit data and let the models answer certain questions or process this data and give you classification results and estimates. And some of you might want to work with more advanced type of models and develop their own neural network, or work on just sort of issues that are related to lexical similarity and text similarity and so on. I'll show you how you could pull word embeddings from different models and either use them in machine learning classifiers yourself that you develop, or just use them as an exploratory tool to identify whether you could get certain similarities between texts and lexical items to match your question, your research idea, or your goals that you want to implement. And so what I'm using is just Python and Jupyter notebooks, and we'll use some API endpoints that are provided by companies like OpenAI, Anthropic, Hugging Face, Voyage AI. And those are, of course, they require a subscription. In the past, these companies would give you some credits so that you could test the models. They might still do that. I'm not aware of that right now because I'm already using them for so long. But in the worst case, you might have to pay for some experiments, or we might have to look for a sponsor if you want to use them. Those are not large amounts of money that have to be invested in using these models. It's just some bureaucracy that is connected to that, to register and get some funds on the account and so on. We can talk about that and then with the teams who are working on solutions. And we'll look at some sample data for general NLP sentiment analysis, and then text classification, and look at some like picked out samples from the anti-Semitic data sets that the team here provides for the Datathon and Hackathon. Okay, so from that, we'll just jump directly into the Jupyter notebooks. Like that again. I have put some agenda here in the README file that you also see on the website of the GitHub repo. So we can go through the Python NLTK type of approach, just extract text and frequencies and generate a frequency profile for the terms in the text. The Natural Language Toolkit, NLTK, is an open source module for Python, and there's a website. I should actually add it here. This is the nltk.org website where you can read about it. The book is available on the website, and instructions how to download and install the module and how to use it. I will update the README after this session. So if we go into that notebook, so this particular one is Python NLTK text and frequencies. As I said, the goal here is basically for us to extract a frequency profile from text and work with it. So in this case here, for example, I'm just using a novel, a book from The House of Pomegranates, that you can download online. The whole collections of books are available on various sources. The first command here basically just says in the data folder, there's a House of Pomegranates text, and I'm reading it in, and I'm just using an UTF-8 encoding of the text. And I can print now the first 300 characters of the text. And this is what you see here. And what we can do is we can import NLTK, and then, for example, just normalize the text, lower it so that we get one token for the only, and so on, so that we don't have, you know, uppercase words, lowercase words, first character uppercase, and so on. They all get conflated into one model when we compute the frequencies. Here, I'm just telling NLTK to give me a frequency distribution of the text, and I can print it then. And what it tells me here, for example, is that I have 39 samples and 174,000 outcomes, which is interesting because these 39 samples now are actually what? Well, they are characters, because I just told it to process, generate me a frequency profile over the text, and the text is a set of characters. And so what you see here now is basically a frequency profile of characters, and you know in English, E is the most frequent character, and so on. So this gives you already a fingerprint, but we are not necessarily interested in that. We are interested in generating frequency profile over words. Here's just basically the discussion and the examples how to relativize these frequencies to convert them into maximum likelihood estimates, frequency-based likelihoods, probabilities that we can generate. And there's things we can do. We can measure entropy, which means that basically it's a measure of how dense this distribution of characters in this case would be. And the entropy is a measure that is an information theoretic measure that you might want to read about. There are links to Wikipedia pages in this notebook. This is not what I'll go in detail into here. For switching from characters to words now, basically what we need to do is we need to tokenize the text. So the House of Pomegranates here is now submitted as a parameter to the word tokenizer in NLTK, and what we get back is a list of tokens, and we can actually print out, say, for example, in this case here, the first 20 tokens, right? And you see that it does the splits and removes punctuation marks and so on. And we can now generate a frequency profile over this token list, and we now have 4,009 samples and 38,000 outcomes, which actually means we use in this novel 4,000 different words, and we use them all together 38,000 times. So this novel just has 38,000 tokens or words in it. And the vocabulary is not very large, actually. It's just 4,000. You know, an average native speaker of English probably has more than 30,000 tokens in the active repository or cognitive system. We can now pull the items from the frequency profile, and here's just the first 10, the frequency profile generated in the same way as we did it with the text over the characters. In this case, we are using actually tokens from the token list. And we see now that words like occur 673 times, house 26, and so on. Words like young and king are also very frequent in this case. So we can build a frequency profile and print it out word by built a frequency profile by printing the token and then the frequency next to it. And we can say, for example, that we can pull the stop words like function words, pronouns, articles, and prepositions, and so on from a list from NLTK, and we can remove them all from this data set. And then we can sort of have a clean list of just word tokens, for example, that might be semantically relevant. And we can now create a bigram model. Say here in this case, NLTK offers us an n-gram model. We can give it the list of tokens and say we want to have two next to each other, which means that we are moving a window of two through the text, one token at each time, and then generating a list of those pairs and count those two, for example. Did I not do something up front here? Just repeat that here so that we get the stop words. Oh, now we have the pairs. So you see we have a list of bigrams, the first 20. So a house, house of pomegranates, and so on. And we can now see that we have like bigrams is actually one less than the number of tokens. This makes logically sense, right? And we can now build the frequency profile. And we see now that we have 17,000 different bigrams used in this text, and altogether 38,000. And we can also relativize those bigrams now and count the frequency and then relativize it to get sort of an estimate of the probability. How likely is it to see some bigram like a house or the young and young king and so on, right? And this might be interesting when we are studying basically tweets and text in general. Tweets are smaller, so this won't be like a big profile actually of frequencies that we observe. So we could treat tweets maybe as just bags of words and look at what kind of words occur in tweets and text that might help us classify this. Here I'm basically just relativizing and sorting this, and I'm getting things like pomegranates, king the, infanta the, star child the, I have no idea, some pairs of words that occur next to each other. And we can sort that by frequency, and we see that of the and so on, such function words are very frequent. So it makes sense to remove them to get actually a better picture about real content words that occur next to each other. Like young king, for example, would be a very likely word pair. And so this is what I did here in the end. And in the end, just removed function words and stop words, and you get young fisherman, young king. Some old function words, old English function words still in there. We would have to extend this. The function word list in NLTK is just modern English. But some of these word pairs tell you basically already what this novel is about, right? And so this frequency profile is serving us basically as a model as the base for probability for a probability model that we want to use in how do I get back to this window, man? I mean,
I think you need to close.
Yeah, so show video panel. So you can speak up, say something. What do you want to ask?
Yeah, I've got a question, Damir. So you're suggesting that we run, for example, these kind of models, take the data set that we have, run this over the ones that are classified as anti-Semitic, and then also run it over the data that's classified as non-anti-Semitic, right? And to see what comes up, and then to use this as a model to find to detect automatically if
Exactly. So
right? So you
this
do
is
that
exactly
differently for the yes, Lisa and Semitic tweets.
yes.
You see what kind of word frequencies are in there and some other similarities, and you do the same thing for the non-anti-Semitic
That's
tweet,
right.
And then you need to
That's right.
combine it somehow.
Right.
Mhm,
And
yeah.
so here's this example that this is the next step. Basically, you already anticipated the logic behind that. So we now what we can do is basically take these corpus text data sets. Here's just some very bad type of spam text that I collected, and you already see some of the core words that spam mail would contain. Now imagine you built two classes here in this example. I'm just using spam and ham, but you built two classes as anti-Semitic and non-anti-Semitic texts, and you can then create this data set as collections. And in the ham section, I now have 1, 2, 3, 4 emails that are not spam, and I have one spam email as an example. And I can now estimate how likely is it, given this data set, I have 1 of 5 texts is spam and 4 of 5 texts are ham. So how likely is it to pick one of those, spam or ham, if I randomly pick a text from this corpus, right? Mm-hmm. So this is an estimate that we can now do, and we can access those in these text lists, and I can normalize them as I just showed with the novel. I can lowercase each single email to normalize the text to avoid reduplication of uppercase, lowercase words, and so on. That's not without problems, though. The normalization has issues, of course, but that's an approach that people apply quickly. And then I can use the NLTK tokenizer, and I can do the same thing, build frequency profiles for the different text types, and have ham and spam as frequency profiles, where I basically have the list of words that occur in each subset of the corpus or data set. And now I can use these frequency profiles, relativize them as probability distributions, as a probabilistic model. So now here, for example, I'm just sort of printing out the spam tokens with the likelihoods for each single token in the corpus. The corpus is, of course, small and won't be significant. But now what I can do is I can use the Bayesian equation or Bayesian approach to compute the likelihood that a certain text that I do not have in my corpus, that I haven't seen before, is spam or ham. And in your approach here, it would be, is it anti-Semitic or not? Here I have a probability distribution of 20% likelihood to pick randomly a text to be spam, 80% to be ham. And I can then get the frequencies here for the individual tokens in the different models and relativize them, so they are now corresponding to likelihoods. And I can take an unknown email like this one here. Dear Hans, I have not seen you for so long. When will you go out for a coffee again, and so on. And I just tokenize it. And what I do then is basically just break it into tokens and then take word by word from this email. And I'm asking, what is the likelihood for this word to occur in the spam mail or in the spam frequency profile? And I'm getting this frequency. If it doesn't exist, I'll just return something like 1. So it's like, or 0, that it doesn't, I don't want to zero out my likelihoods. But what I'm doing here is I'm multiplying the likelihood of each single word occurring in this unknown email using the spam probability distribution. And then I will do that same thing using the ham probability distribution. And then I can compare those results. And the one that gives me the maximum score is the winner, and I can use that to classify my email. So here in this case, this is exactly what I did for spam and ham. And now the prediction in this case is that the email is spam. So the classifier is not that good because probably we have too little data in it and so on. It's not maybe using the right words. It's not normalized in the best way, but you could all do that. Go ahead, Günther, say what.
Yeah, let me try to break this down in easy words. So first, you try to if you go with the tokens, you try to see for each token to develop a probability of a word or token. This is likely to, in this case, spam, or this is likely to be anti-Semitic in an anti-Semitic text, and this token is likely not to be an anti-Semitic text with some probability. Then you get a new text, like say a post, a tweet, let's say, that you don't know if it's anti-Semitic or not, and then you run word by word. Is that more likely to be in an anti-Semitic message or more likely to be in a non-anti-Semitic message? And then you add this up and you get a score, right? And then you determine based on this score if it's likely to be an anti-Semitic message or not. So that's a simple token-based model, right?
Right.
Good,
So you should think theoretically what that means is the frequency profile that you generate for words in spam mail and the frequency profile for words in ham mail, in non-spam mail, you could think of them as functions. And you have now an unknown text, and what you're asking is how likely is this unknown text generated from the spam function or from the ham function, right? And what you do for that is just take word by word and multiply its likelihood taken from this particular model and sum up, multiply all of these likelihoods of the words. What we are doing here is just simplifying that. We are summing up the log likelihoods. That's another strategy to just sort of keep the scores manageable. If you multiply very small numbers, probabilities of words, in the end, in the computer, it will turn into zero, very likely. And then you have two scores, and you just say which one is larger. So this is minus 132 and minus 155. So the spam, unfortunately, for this email is larger. We could improve the results by extracting a better frequency profile over larger data sets. That's just one classical approach that has been actually implemented in all the email software a long time ago, 20, 30 years ago. And it's a very common classifier.
And this, by the way, might explain also why automated detection has difficulties in messages that call out hate speech or anti-Semitic speech.
Exactly.
Because if you just go word by word probability, then if somebody calls out, this model cannot really predict it. And there are now, I think you will move to more complex models soon, but this is an issue with this kind of fully token-based model.
Exactly. So this is the reason why you might want to use, and this is why I wanted to introduce some natural language processing pipelines to actually maybe have the power of real NLP to analyze the content, so that you could differentiate between calling out anti-Semitism and real, true anti-Semitism. And so one of these pipelines, my favorite, is developed by colleagues and friends in Germany, in Berlin, Spacey, and another one, Stanza, is developed by colleagues and students at Stanford University. I'll just briefly show you how they work and what they can do. So Spacey is basically explained here. There's a website where you can go and read about how to set it up on your computer, on your particular computer. On my particular computer, I want to use it with CUDA, and I want to use transformers, modern neural network architectures, and so on. And I can install language models, and here are some listed. So there's English Core, based on a web corpus, small, medium, and large. So the suffixes SM, MD, and LG tell you about the size of the model. The larger the model, the better it might be for a certain task. The prefix EN or ES here indicate the language. So they use the ISO 2-character language code for the models. Now you can go on the website and see what models they have, and they actually do have a lot of languages supported there. So running such a model like spaCy just basically requires two lines of code. Load the model in Python as here, and then once it's loaded, you can load a language model. So in this case, I'm just testing the Spanish small model just to show you how that works. And I can then put in a text. This is my NLP pipeline, and I submit to it a text like "¿Cómo estás? Estoy bien." And I get a doc object back, and now I can run an extraction from this doc object. It's token by token, so it gives me the word and the lemma of that word, right? And that's already useful, so you can lemmatize instead of just lowercasing text and brute force normalizing it. You can now actually convert the text into the token list into a list of lemmas, lexical base forms, and this way have maybe a much better base for classification. But you can also extract a lot of interesting information about every single token. So in this case, for example, I'm not only extracting actually the lemma for every word that I put into the text. So the first column here is the token. The second column is the number here. This is the character offset in the text. So from 0, the word como starts, and then I get in the third column the lemma, then I get part of speech tags, and I get dependency graph information. And I'll say a little bit more about that in a second. And you can then also ask, is it an alphanumeric string or sequence, or is it a stop word or not? This is the last two columns, for example. And why is this interesting? Now here I can actually do the dependency path tree, and I can try to figure out what the elements in the sentence are. So estás is marked as the main verb, and it has a specific relation to como and so on. This is now, for some of you who don't know Spanish, maybe cryptic. This is why we'll switch to English, and I'll just load the English model now and apply it to this text here, which says John Lee Hooker loves Ali Hassan Kuban when driving on the highway. That's listening to Ali Hassan Kuban. And so what you get here is you analyze this text and you can now extract entities. So you know that John Lee Hooker is a person and Ali Hassan Kuban is a person too. And I'm pretty certain that this model has not been trained on any text that contains this sequence of words Ali Hassan Kuban, because Ali Hassan Kuban is a famous Egyptian musician who is playing actually only on traditional weddings and so on. So it's not something very popular, in particular not in the Western world. And I can expand this and process something that contains far more of these entities, and I can print them out. So you see now that Apple Inc. is labeled as an organization, California is a geopolitical entity, and so on. So you can now go through text and label entities. If somebody mentions somebody by name or a country or a place and so on by name, it will be automatically labeled, hopefully with a high accuracy in these models. I'll skip over these matching parts. Those are not very relevant. Just read it yourself. We'll use the dependency parser to show some more possibilities. And there's a visualizer part of spaCy that it's called displayCy. And we'll use now a very large model. So this one is a transformer model. It's one of these more modern neural networks. And we can process a sentence like Peter bought a car and Jane bought a bicycle. And then what you can do is you can visualize the sentence structure. And what this visualization tells you is that bought here, for example, the second word is the core word. It's actually the root predicate of the sentence. and Peter is labeled as being the end subject, the nominal subject of this verb, which is useful information because sometimes you have to sort of try to understand what is this predicate referring to, or what is a very negative adjective maybe referring to. So you want to extract what is the object. Like here, it labels car as being the object of buy or bought, and Peter the subject. And then there's a conjunction to another bought in the second clause, and Jane is the subject there, and bicycle is a direct object there. So extracting such relations helps you basically focus on core relations. What is this clause or sentence about? What is the subject? What is the object? To basically maybe go around problems of calling out versus being really anti-Semitic and so on. And here is some other visualization tool where you can use text and then just display or render in color with labels the entities contained in the text. And we'll get back to the vectors later, actually, because we'll discuss these embeddings as well. So this is just to show you there are linguistic tools that can do advanced annotation and processing, that can parse sentences into core elements, that might be useful for all kinds of detailed semantic analysis of the content. Stanza, just quickly, similar thing. That is also used in a similar way. I import the stanza model. I use Spacey because stanza doesn't have displacey to show the sentence structure. I built a small function to actually map stanza output into Spacey output. Here's just the way how you download the English model. And you see that it's using Hugging Face. This is a website and a company that shares all kinds of language models. It is very proud to have, I think they said that they have reached 1 million language models already on the website. Maybe it's just 100,000. But you can find a lot of different models on this website, Hugging Face, and you can use them without any cost. Sometimes if you want to use them on the platform itself, you have to pay for that. Good. So this downloaded now the big language model, and now I can actually instantiate a pipeline, and I can say this is for English, and I wanted to do tokenization, multi-word expression, part-of-speech tagging, lemmatization, named entity, dependency parsing, constituent parsing, and sentiment analysis and labeling as well. So very rich analytics that I can run now over text. And here's some example texts. The pilot had arthritis and so on, and it gives me the text broken down by tokens into sentences. And I can go now sentence by sentence and analyze the content and check out whether it's a positive sentence, negative sentence with respect to the sentiment and so on. And I can print out all kinds of details. As with Spacey, I can print out parts of speech, and I can print out morphosyntactic properties. Is it a definite article? Is it an adjective? Is it a complex tense form in the sentence, and so on? Gender and number information is printed out as well. So it's a very rich analyzer. And the lemma, of course, in the same way as basically for Spacey. And constituent parse trees, if you're familiar with those, they give you sort of sentence structure in a different perspective. Other things give me the entities. So it gives me that arthritis is a disease and rheumatoid arthritis is a disease. So it can do hierarchical named entity processing as well. And it shows you here sort of a detailed annotation token by token in some standard what named entities are there in the sentence. And here it gives you sentiment, for example. So it would tell you that the first sentence, number 0, is neutral. The second sentence, number 1, has actually a positive sentiment. It's 1. And third sentence, number 2, is also 0, neutral. You would get, I believe the annotations are -1, 1, and 0 is for neutral. And you can do all kinds of other things like identifying the language if some text is actually multilingual. and there is one sentence or one clause in English, one clause in Spanish, you could actually get that detected as well. Here is again the Spanish pipeline. So what we just want to reload is the entire Spanish processing pipeline. Here's a function that I wrote that just maps the stanza output into spaCy standard so that you can visualize the dependency path trees. And let me just correct the sentence so that there's no ellipses in there. And what we can do is basically display the analysis, the sentence path tree. So loves, in this case, is the main predicate that doesn't have any incoming edge, and its subject is John, and its complement is the verb to read, and the object of read is books, and so on, right? So you get sort of the idea what these dependency trees can give you. That's pretty powerful in some ways. You can really sort of extract real relations between elements in the sentence. That's for spaCy. Go ahead, Günther.
Yeah, I just want to see if I can try to sum this advanced model up in just a few words. So basically, it makes this going from a tokenized model that only has the probability of each token, goes into more complex relationships between the words in there. And also, but again, you use to separately analyze how anti-Semitic tweets come up there if you run these tools, and then how non-anti-Semitic tweets if you run this, and then you take the same probability, then saying, well, what is more likely? Is it an anti-Semitic? Does it compare more to the things that I saw in anti-Semitic tweets or in the non-anti-Semitic tweets?
Yeah, so along these lines, you can do that exactly. But another thing that is powerful with respect to the dependency path trees, for example, just imagine that we say this tweet is not anti-Semitic versus this tweet is anti-Semitic, right? So the one difference is you have a not in there, so you could take this into account, but when you just count the not, you don't know what it refers to, right? It could be like, this is not a tweet, right? But it says it's not anti-Semitic, right? So the not has scope over anti-Semitic, and you would see that in these path trees. What does the not actually dominate, right? So that you can then analyze the semantic reference correctly. This is highly relevant for sentiment analysis. So if you want to analyze basically, is somebody expressing positive or negative sentiment towards Jews in general in this tweet, for example, it's relevant to know what the negation refers to. What do positive or negative adjectives refer to that are used in the text, right?
And also not specific to the object, not in general sentiment analysis. What is the sentiment generally of this message or this tweet, but towards Jews or Judaism, or this is a very different.
So exactly. So it could be
you can have this object included there, right?
Right. So it could be basically that a negative adjective is attached to the subject or the object, and it could then basically, what you want to extract is that this negative attitude or sentiment is related only to this entity, whatever that entity is, right? And so that is an interesting aspect. So this is actually sort of, in fact, what they call aspectual or aspect-based sentiment analysis. You want to extract the details, Imagine you're saying things like, oh, I like this phone, just the battery sucks, right? So you're saying in general, the phone is fine, but you've picked one specific detail, the battery, and you say that it's bad, right? And so this is sort of something that people are working a lot on. And this is exactly taking us to the next phase. And this next phase is basically talking about logistic regression and doing sentiment analysis with that. And I'll just go through this quickly and explain a little bit what this has to do with and how we could use that in this context. with anti-Semitism and tweet analysis. So this here uses a very interesting instrument that is very common actually in sentiment analysis. It is that people developed lexicons and dictionaries where they store lists of words and they associate them with negative or positive attitude or sentiment. And what you want to do is basically take such a lexicon and check how many of these positive or negative words are in your tweet or in your text, and take the value that they have for positive or negative sentiment, sum it up, and have a generic type of overview. And you can now, if you use Spacy or Stanza, you can actually parse out the subject and the object and check how many times a specific subject has a negative or a positive sentiment associated to it using such words from the lexicon. The lexicon as such, you will see that here, comes with NLTK. You can basically install the free resource NLTK, and then on the website find instructions on how to install the data sets, the corpora, and such a dictionary like the Vader lexicon. And here I'm just loading it into memory. So it's going into the resource folder. My machine here is a Windows machine, so it's just going into the updater roaming NLTK data folder, and in there's a file called vedalexicon.txt, and I'm reading it in. And now I can look up the word admirable in the lexicon. So this is allowing me to just search now the Veda data for admirable, and what I get back is a score of 2.6, and then here in this list, what this list shows me is they used 10 subjects, human beings, and asked them how to what extent is admirable a positive or a negative term in terms of sentiment. And the subjects responded with these numbers. So one subject said 2, the other subject 3, the other subject 4. And what you get then is a variation over these numbers, and the variation of variability is 0.6. But the score that we are interested in, we are not interested in the rest of the data here. We just need the 2.6 that tells us at a level of 2.6, this admirable was judged to be a positive term, right? Negative terms are going into the negatives. They are minus terms. 0 terms are neutral. They are not associated with any kind of sentiment, negative or positive. So annoying, for example, this is the other example here. Let me just pull that so that we see that it's really running on the code, is judged to be minus 1.7 negative, right? And so now what we can do is we can pull certain tweets, and we can basically go through the tweet and count how many times did I see a positive or a negative adjective or term in there, and I can also sum up the negativity and the positivity scores and so on, right? What I want to do here is basically I'm now actually collecting information about each single document, right? So this is just to show you that I have this Veda lexicon and I can collect information about term sentiment from it and use it. There are a bunch of other resources. You don't have to restrict yourself to that. And what I want to do then is I want to collect for every single tweet information and represent it in a vector form as a numerical vector. So here, for example, I'm tracking now for every single text the number of positive terms in the text, the number of negative terms, 1 if there's a no in the text, 0 if there's none, the number of pronouns, all variants of first and second person, 1 if there's an exclamation mark in the text, and 0 if there's none, and the log of the number of tokens. So this is basically just, it's clear. The first number of positive terms, just I want to know how many positive terms are in there as a property of every single tweet, right? How many negative terms? I want to know whether there's a negation used. Negations are usually indicators for I don't like it, it's not nice, it's not good, stuff like that, right? If I'm using pronouns, the idea here is if you're using first and second person pronouns, that's an indicator whether you like something or dislike something. And the more you use such pronouns, the more information about dislike or like it gives you actually. And exclamation marks are indicators for you're really excited. So you could use other features like do they use multiple exclamation marks? Do they use you count these exclamation marks? Do they use certain kind of emojis and so on? You could count those too, right? You could think of ways to put these bits of information together that represent your tweet, and then you want to come up with an analytical tool with a classifier that uses this information. This is now a supervised handcrafted feature extraction or feature modeling of tweets, right? You actually have studied tweets, you know how they work, and you extract these properties, and you hope that knowing these details about every single tweet will give you enough information to classify them correctly. And you can expand that, as I said, you can pick other features and properties and so on. The log of the number of tokens is just sort of a relative scaling factor. If the tweet is very, very long, so imagine there's no limit on the size, it could be like multi-page text, then the number of exclamation marks is very likely going up, and the occurrence of a negation and stuff like that. So it would have consequences for the other values and scores, and hopefully a system can actually learn that and be trained on that. And what I just did here is take this text above the criteria and say, here's a function, and you submit to it a text, and this is exactly what it does. It goes through the Veda lexicon and sums up the scores for negative terms, the scores for positive terms, checks whether negation is in there, checks whether any of the first person, second person pronouns is in there, and returns a vector that represents this tweet then, right? And so here's a sample text, it's okay and so on. So this is a real sentimental text that has sentiment in it. And I can run it through the function. And you see now what I get back is 4, 2, 1, 3, 0, and 4.2. So the first 4 is, go back to the thing here, how many positive terms are in the text, right? And now positive means I don't even have to know them, because what I just did is actually I asked the Veda lexicon, that data set that I also put in the data here on the system, to tell me that. It just goes through the text and counts for me the number of good terms, positive terms, 2 negative terms. There's what does the third value say? There's a no in there. So there's a 1 in the third position, and so on. So get the idea? So I can take each single tweet and generate for it such a vector representation. And then what I could do, so this is just taken from the textbook that I was actually pointing out on the first slide. And this is the weights that they start with. And this is just running a sigmoid function over the dot product of the weights and the input vector. Read this intro to logistic regression to understand what that does and how that works. And what we then can compute is, what is the likelihood for this text that we just looked at to be positive or negative? And we get 96% likelihood for it to be positive and 3% to be negative, right? So this is basically just a simple logistic regression type of model. Now, what we can do with that is we can learn the weights. So what that means is we feed into this model a lot of sample tweets that have a label, positive or negative, that you guys generated, you labeled these tweets, and now we can make it learn as a classifier. And I'm not going through this training phase because it can last like 15, 20 minutes on my laptop here, but it explains how this learning works here in this notebook. And at some point you have a ready model and you can now apply it to any kind of text. And it would give you then for each of these texts a ranking and class that it belongs to, positive or negative, And you can use, to abbreviate that, this code above is just my handcrafted code that shows you how to implement that manually. You can just use an existing library, which is scikit-learn, and save yourself from doing this kind of labor of, coding everything yourself. It's just call one function, call count vectorizer and train test split function in scikit-learn, and then run a logistic regression training phase yourself. And what you get back is then a model, and you can use it to predict for a specific test set that you want to evaluate the label. And in the end, it tells you what the accuracy is. So for this label, this was the Amazon sentiment data set that is basically just a list of these tweets, of these comments in the products, attached to the products in the Amazon shop. It predicts 88% correctly the labels for these kind of texts, which is pretty good for such a small set of features that we extracted for it and trained on. Okay. Any questions with respect to this kind of approach? So this is handcraft your properties yourself, use something like logistic regression from scikit-learn, and train a model to do that classification for you. Nobody is asking a question. Okay, so now we can go to the next phase. There's another tutorial, document classification tutorial, that you can look up. You can study yourself. I'm not going into that. I'll show you now a more modern approach, which is transformers. This is sort of this new superior type of technology used in large language models and so on. But famous language models like BERT, for example, are based on transformers. And I'll just show you how to quickly use it without any effort to do reasonable solutions for you with it. So you import basically the transformers library. You have to install this module for Python on your distribution. And I'm importing the pipeline from the transformers. And I will tell it that I want to have a pipeline that uses zero-shot classification for the Facebook model BART, which is similar to the BERT models. It's a large language model that Facebook shares with us for free. And what I can do here, when it says zero shot, it means basically that I don't even train that model. I just give it some data and I ask it a question, right? And so in this case, I'm saying, here's a sequence, here's a list of words, which is a sentence or a paragraph for us, right? And it says we like to use code for Python, but Vim for C. Code is a whatever, Microsoft Visual Studio Code. This is what it means. And the labels that I want to associate with this text are given below. So this could be class labels. In this case, I want to say, is this text automotive? Is it about programming? Is it about politics? Or is it about economy, right? And that's sort of how does the model do that? Well, the model should know something about what automotive means. This is what these large language models actually are trained on. They are basically able to associate a certain text with the meaning of the individual words that we provide as labels. So if we would provide it anti-Semitic or Islamophobic or whatever, such labels, and then give it an example text, it would tell us what of these labels is best associated with the sequence of words with the example text, right? That's the idea. And it should know that because it's trained on very, very large data sets, corpora. And so here now, when I say we like to use code for Python, but Vim for C, it tells me that programming gets a likelihood of 89%. And note, I just downloaded this model from the web in 3 lines of code, and I didn't train it at all. And it's pretty well, and it's pretty good in guessing that this text of mine is about programming. It's just one sentence. So it's like even smaller than maybe, I don't know, the average tweet that we are looking at. So it does a good job on that kind of things. What you can do now is, of course, you can tune these models to be even better. You can tune them on this particular problem, anti-Semitism versus not. And here's another example, some sequences of multiple texts. So you could have n tweets in such a list of strings here, and you can run the classifier with the labels that we provided on each of those automatically. And now it says increase in travel demand is one of the causes for oil price increase, and it tells me that the winner for that is economy. An expected poll shows that the party in power will lose seats in Congress. The winner for those is politics, 90% likelihood, and so on. So you see, it's pretty good at doing that, actually. All the others have much lower probability scores, all the other labels that are potential labels for this text. This is pretty cool, right? And so I can also say, give me for each text multiple labels if I have things like texts that could be automotive and economy at the same time. Here, for example, as expected, polls show that parties and so on. So it says politics, 98% likely, economy, 44% likely. Good label for this text. And the others are below 1%, right? So you can generate multi-label, multi-class labels for such a text. In this case, the last one, the party in power may lose seats and so on, is politics and economy. Both are the winners, and all the others are far below 1%. So if you have a threshold for when you think the label should be given to this text, you would say, it should be like above 50% or something, and everything that is below that is not a good candidate as a label. So this is to start with. You could use such models. You go to the Hugging Face website. The link is here, and you can read instructions how to actually even fine-tune this model, which means that you just actually throw in the tweets that we are dealing with. And you can actually also provide labels up front and ask it, what is the association between such a tweet and this label, if you feed it with tons of data of that kind. Okay, so this is getting us to large language models and transformers, and I'll not go into these Ngram models and so on, but there's just a small implementation that explains you how such a next word prediction model, like a large language model like GPT, ChatGPT, or Claude, can be implemented. That's a very simple, trivial implementation that actually still gives you good results. But what we want to do is go quickly into GPT-4 and Claude just to show you how we can actually play with these models and ask them to give us some judgment, for example, for certain classification problems that we're dealing with. Let me just close some of those here so that we get this out of the way, what we just looked at. Okay, so GPT, let's try that first. Just find it. Okay, so now this requires, of course, that you go to the OpenAI website. There's a link that I provide. You have to register there and get an API key. This API key is placed in this file secret.py, which I exclude from syncing with GitHub because it contains my private API keys. But I created a template like this one here. And if you register with any of these services like OpenAI, you could actually put your key in here and rename this file to be secret.py. And then the Jupyter Notebook here would load that and set your key correctly. So you see here, I'm saying you need the OpenAI module, and you load from the secret file the OpenAI API key, right? So let's do that. And what I can do here, I'm just overwriting this. I'm using the 4.0 model, which is the most recent one that was quite impressive, that allows you to do fancy stuff, reasoning, and so on. And I'm creating a client with the OpenAI API key. And this, what that means is basically I can't download this model to my local machine because my local machine is too small and not capable to hold it and run it to inference with it. But I can talk to it remotely. So I'm now establishing a connection between my laptop and the endpoints that OpenAI set up on the cloud, and I can talk to the service. And this function here is talking to the service. It's the call GPT function, and it just sends to the service the instructions and a specific prompt, some data that I want to be analyzed, right? So here, for example, the instructions are answer the following questions, or question, what are the implicatures of the claim I bought the blue car? Okay. And we can submit this to GPT, and this last 3 seconds. The claim I bought the blue car carries several potential implicatures, which are implied meanings or suggestions that extend beyond the literal interpretation of the statement. Some of these implicatures could include choice of selection and so on, right? So it's actually doing smart stuff. It can handle some of these kind of things. Now, what we could do is basically, I have a collection here of some biased anti-Semitic tweets. Let me pick this one here. So we could instruct ChatGPT or GPT-4o here and say, okay, let me just not to lose this tweet. And then I could give it instructions. So in the following, I will give you sample tweets and ask you to provide detailed answers about them. Okay, so this is the instruction. And then here I can say now, I read this tweet. Is it anti-Semitic? Okay. So let's see what it does. Determining whether the tweet is anti-Semitic involves analyzing. So I could actually, I can say, don't give me explanations, just a yes or no. Okay, so if we submit this now, it just says yes. Okay, so this is anti-Semitic. Let's take another tweet according to GPT. So here's one that is not biased. And sorry for this. This is reality. So this contains some bad words, the F word twice even, and some Esh word, and it should contain some kike word as well. So this is pretty bad. But actually, this tweet was not judged to be biased. It was just calling out and reporting anti-Semitism. So let's just remove some new lines here. I didn't prepare that up front. Sorry for that, but just to make it easier for this model and the system. Okay. And then I don't know whether actually ChatGPT will fire up some filter and say, I'm not answering that, but let's try it out. And it says yes. So in this case, let's try again so that we are certain that it actually does that. It says yes, and this is wrong, actually. So you see that it says, oh, what I should do is maybe add a different type of quotes for reported speech. Maybe this is confusing the model. And it's still yes, so it didn't help. And so it has issues with reported speech and calling out, obviously. in this one example. We could try another one. So there's a smaller one here that just says that there's somebody is calling this word out in front of a store. Let's just repeat that. And it's also saying yes. So we could continue with such evaluations. I mean, you could play around with instructions. You could actually do the following. This is called a zero-shot approach. You're giving a context and you're asking a concrete question and you're giving a data sample to the model. What you could do is actually provide the model with few-shot or n-shot examples, which means that you give it a list of examples where you say this one is anti-Semitic, this one is biased, this one is not, and you could then train it or tune it to improve the answers, right? The idea. Same thing is basically. Claude 3 is just the counterparts. This is Anthropic. Some, I believe, developers from OpenAI left and started a new startup that does the same thing. So again, I'm just loading the model, establishing a client with my API key to the endpoint from Anthropic. And here I'm testing just respond with 1 if the claim is true and with 0 if it is not. The following sentence contains an ellipsis and it's just returning 1, and it's John bought a car and Mary a bicycle. That's true. And you can actually bias these things. Now there's no ellipsis in there. I could actually give it instructions that say things like, let me just give you an example. Line, assume that you are a world famous linguist, for example, or Chomsky, right? So it can do that. So you can actually change the judgment if you change such instructions and bias it to take up a certain kind of personality profile, for example. Right. So if I remove this bot, then what we have here linguistically, we have a VP ellipsis or gapping construction, whether this is what it's called. And now it's detecting that, yeah, it has ellipses in it, right? Good. The other aspects are basically you might actually want to work with vectors, and vectors, for example, are sort of things when we process text in these modern systems and transformers, we can't put in strings there or words in these neural models and the transformers. What we do is we replace words with vectors, and these vectors, here is an example of a model that was developed by the colleagues at Stanford, have, in this case, for example, 300 dimensions. So these are vectors trained on text to reflect semantic properties of words in a semantic space, n-dimensional space. And what we do is we use these vectors to reflect semantic properties that you see here now mapped into 2 dimensions. So say, for example, brother and sister are sort of similar in distance to uncle and aunt and man and woman. They should be sort of more parallel if the semantic space is well formed. But this could be also from the conversion of 300 dimensions to just 2, resulting from that. And here are other examples where you have things like slow and slower, short and shorter are actually real parallelograms. They are equidistant. And this shows that sort of certain semantic properties are represented in these vectors and mapped in there. And you can use these vectors now. You can actually use models that give you these vectors. So here, for example, this is just using bird, and I can I will have to use transformers and the bird tokenizer and the bird model. This is just sort of to help random seed the PyTorch module, and I'm getting embeddings here in this function. So here's my instantiation of a tokenizer and the model, and here's my word list. And what I want to do now is just for each of these words, I want to ask BERT, give me a vector that represents that, right? And here now you have each single word and the vector that goes with it. And what I can do now is I can not just submit a word, I can submit to this function actually a text. And I can submit to it lists of texts that are, say, for example, anti-Semitic. And I can then submit and lists of texts that are not anti-Semitic. And I can then submit an unknown text, and I get a vector back for this text, and I can compute the similarity between the anti-Semitic and the non-anti-Semitic text by just measuring the distance between the vectors that these texts represent. And that's another approach that you can play with. You can use these vectors also to train your own models and so on. I will not go through the other details, but there's an example of how you can use entropic vectors. Entropic is using the company Voyager that is doing the vector model for them. And there is an example how to use the OpenAI vectors, and they all have different properties, but you get an idea these vectors could be giving me a vector representation of a text, and then I can use that to compute similarities by just measuring distance in linear algebra. Good. So that is that much for today. I shared all the notebooks on GitHub and the examples, and I'm happy to discuss with some of you in your particular projects issues or how to use these in a specific way. So open for discussion and questions now or later, anytime when you're working on these projects.